Hi, this is part 2 of the physical quantity review. We left off in the last video talking about displacement. We're going to move on to another measure routinely used, or quantity routinely used in speech science, and that is the term velocity, or the measure velocity. And velocity is a rate measure. It tells you how quickly something changes, or a rate basically tells you how much change there is in a given unit of time. And you can see by the equation that v, which is velocity, equals x over t, where x is or more often displacement, which is a vector quantity, per unit time. We can express this with a varying time base, and we could have it over a fairly large time base or over a very short time base. For example, if you are trying to measure the velocity of your car drive as you move easterly from one town to the next, if you could measure your average velocity over the course of the trip. If you drove 70 miles and it took you 1 hour, then your average velocity would be 70 miles per hour, and that's a useful thing to know. But you also recognize that your velocity at any given moment in time was not necessarily always 70. You weren't producing a constant velocity. In other words, the instantaneous velocity could have varied quite a bit over the course of your trip. The magnitude of that is expressed by the speedometer on your car, and so you know that you typically will be speeding up and slowing down along with the traffic. So in the case that we can learn what the average velocity tells you some information about how long an event was, what the average velocity of that event was, we sometimes are interested in knowing what's happening on a moment-by-moment basis as well. Common units for velocities in speech studies, at least with regard to structural movements of the speech structures, are typically measures such as centimeters per second or millimeters per second. Now there is a distinction to be made between velocity and speed. We also use these interchangeably in common language, but speed simply refers to the magnitude portion of velocity. If we believe velocity to be a vector, it's going to have a sign or direction associated with it. Speed is simply the number, the amount. Your car speedometer tells you how fast you are going, but does not tell you the direction that you're going on. And so it's a good way to remember that. We also use velocity in measuring the amount, how volumes of air move through the speech mechanism. We sometimes call this flow or airflow. We also use the term volume velocity to denote that what we're measuring is a velocity, but it's of a volume of air. This is commonly used to measure, air as it's drawing into your lungs or moving out of the system while you're on the egressive phase of respiration for speech. I'm going to show you the original plot we showed earlier of the jaw changing position with respect to time, and then an instantaneous velocity trace along with this. And if we focus our attention on this initial or early upward movement from here to about here, where the mandible goes from a extreme low position to an extreme high position, and then drag these lines down, we see that this upward displacement has a bell shape to it. Notice that at the lowest position here, just for a moment as the mandible is changing direction from a downward movement to an upward movement, just for a brief moment in time, the velocity of that mandible is 0. Then as the mandible begins to rise, there is a speeding up, or an acceleration actually, of the structure to a point where right around in the middle here, where it's at its steepest point, we reach a maximum velocity. Then what happens is we begin to approach our extreme position, we might want to call it our destination, we begin to slow down. And this is analogous to just what we might do if we were moving from one stoplight to the next with our car. We're going to press on the accelerator till we get to a maximum speed, and then we need to decelerate or slow down coming to a stop again. And as we get to the extreme position, velocity very quickly goes to 0. Now remember, velocity is a vector quantity. So in this case, we use this is a positive velocity that's associated with the positive displacement. If we look over here at our downward movement, it has a negative displacement, and as you see here, we also have a negative velocity, so the sign carries through. Now we've used the term acceleration already, and acceleration simply refers to a speeding up or a slowing down of a structure. We refer to speeding up as a positive acceleration or slowing down as negative acceleration, and it is also a rate measure, but this time it is the rate of change in velocity. So acceleration is velocity over time. If you remember, velocity is displacement over time, so its acceleration is displacement over time, which then converts into distance over time squared. So the acceleration units are typically meters per second squared, often in SI, but it could be centimeters per second squared if we were using a CGS system. And just as velocity can be expressed as an average or instantaneous phenomena, so can acceleration. Just to quickly show you an acceleration trace along with our velocity and displacement traces, we can take our line here down and down here, and you can see that what we have is both a positive acceleration as the structure is speeding up, and then a negative acceleration as the structure is slowing down. Now, force is a push or a pull on an object, and it is related to acceleration through Newton's equation F equals ma, where force equals mass times acceleration. And this is easy to understand. If you have a structure or an object that has a given mass, and you want to accelerate that mass, you need to apply a force to it. And the force needs to be proportionate, will be proportionate to the amount that that structure or object will accelerate. Alternatively, you can think of an object that's in motion that's accelerating, a bowling ball, for example, that's accelerating along the floor, and it hits a wall. It will apply a force to that wall, and that force will be proportionate to both the mass of the bowling ball itself and the acceleration, its acceleration when it hits the wall. We have units for force, newtons in the SI world, and terms like dynes. Many times, there are many other, I should say, terms for force. Since acceleration, like velocity, like displacement, is a vector quantity, so is force. And we had mentioned this before, that force is, to understand force and its effects on a system, it's important to recognize that we need to know both the size of the force, its magnitude, and also the direction upon which it's acting on the object.